Hello. So I want to talk today a little bit about the idea of limits. Informally, it's just a value that a function approaches as the L, the value that the function approaches as the input approaches some number A. Um, it could be, that's exactly what I have written here. It can be something smooth. A nice, well-behaved function like this. And you can imagine, x is approaching A, either from the left or from the right. And as the x value approaches A, you can track the points on the graph. And you see that the y values of those points will approach some number L. It could be some sort of smooth function, or it could be some kind of crazy discontinuous function. Maybe with lots of oscillation and holes and all sort of strange things happening. But still, as long as the y values approach L as the x values approach A, we would still say that the limit exists and equals that number L. So notice it's just as x approaches A. What happens when x equals A is immaterial, right? Is not important here. For this definition, for the idea of limit, it's just as x approaches A, does f of x approach L. That's all we're concerned with. So this is kind of the informal definition of limits. It works fine to think of it this way in simple cases. It's also important to have a more formal definition, especially for strange cases where it's maybe not so clear. So this is the formal definition. This is taken from basically from the work of Cauchy in 1821. He had a very, very, very important textbook basically for his course on analysis that he taught. So from his book, this is the formal definition, and this one is maybe quite a bit more intimidating when you first see it. So that's what I want to focus on today to get an idea for what's going on there. So let's again consider the same expression when we write x approaches A, limit of f of x equals L. Right, I want to define it in a much more formal way. For every positive real number epsilon, I'm going to sort of draw the definition as I write it here. I'm going to draw it in kind of a nice case. So here's L, here's A, and I'm going to say for every positive number epsilon, epsilon you want to think of as some allowable error tolerance in the y coordinate. And we're going to say that for every epsilon, there exists another real number, delta. And delta is going to be some corresponding error tolerance in the x coordinate. So delta is going to go a certain amount to the right and a certain amount to the left from A. And what do I mean by allowable? I mean that as long as some x coordinate is within delta of A, right? So as long as you pick any x value within delta of A, then the corresponding f of x values will all be within epsilon of L. Right, so this is the formal definition. Yeah, so just basically traces back to the ideas of Cauchy. So here, what I want to do is give this maybe a little bit more, it's pretty abstract, it's pretty symbolic, give it a little more concrete of an interpretation. So sometimes it's nice to think of kind of a lab measurement sort of setting. So think of L as some quantity that you'd like to compute in a lab, in a science lab, in a manufacturing process, whatever it might be, right? Right, so it's going to be some computed quantity, right, using the function f. And we're going to think of A as a measured quantity. So A is something that we're going to physically perform a measurement on, whereas then L, via some formula f of x, L is some quantity we're going to calculate based on this measurement A. So the question is, if we know, if we're given some required level of precision on L, right? How precise of a measurement do we need to take on A? And what's nice here is you can think of epsilon as the required precision on the output, right? And then delta then is the corresponding precision on the input. So this is, it's interpretation. Obviously, it's not directly part of the definition, but I think this is a good way to think of epsilon and delta and make it a little more concrete. So let's do a really specific example. So for example, we have a thin material that's wound up in a roll. So just like a roll of paper towels. And we'll say this is 4 feet high. So the 4 foot high roll of this material. And then what we're going to do is we want to unroll 12 square feet of material. And for our purposes here, let's say we need it accurate, the amount of actual unrolled material, we need it accurate to 0.1 square feet for whatever purpose we're using this material for. Then the question is, how accurately do we have to measure the length of material that is unrolled? And we're going to assume it's exactly 4 feet high, right? But the idea is, given this as exactly 4 feet high, we'll spot ourselves at that assumption. We're going to unroll some amount of it, right? And we're going to take a measurement here on, not the scale. 3 feet is less than 4 feet, isn't it? There we go. So we're going to unroll 3 feet of it because I want 12 square feet total, right? But as we unroll it, exactly how wide is that? Well, it's going to be, 3 feet plus or minus delta is how much we're going to actually unroll, because it's sort of real world setting. So, maybe we unroll 3 feet plus delta, maybe we unroll 3 feet minus delta. The whatever tool we're using to measure that 3 feet only has limited precision. So, but regardless of that limited precision on the tool, I want to make sure that I have this amount of accuracy on the square footage, right? That it's exactly a tenth. That's no worse than a tenth of a square foot off from this desired amount of 12 square feet. So that's what I want to figure out. So here's what I can do. I can say let x be the number of feet unrolled of the material, right? So the width of the material that we unroll, or the length, however you want to call it. Then you can say, okay, f of x, you can imagine if you unroll x material, well then 4 times x is the area. Right? So really what we're being asked to do here is we're being asked to find delta for L equals 12, A equals 3, and epsilon equals 0.1 in this definition, right? So we're saying let's graph the area versus the length unrolled. Right, so if I don't unroll any width of material, then I have 0 area. So it starts at 0, 0, right? And then it comes up with slope 4. Right, if you unroll 1 foot, you get 4 square feet. If you unroll 2 feet, you get 8 square feet. If you unroll 3, you get 12 square feet, and so on. Right, but this 3, this is what we really want right here, because we're looking for 12 in the area, right? That's going to be our L at the value of 3. All right, so this will be A equals 3. And now what I want to do is I want to find that delta. So what this amounts to at the end of the day is really just solving for a couple intersection points. So I'm going to zoom in on the part of the graph I really care about. And I'm going to purposefully draw it not to scale, just to be able to see it a little bit better. So here's 12, 12.1, and 11.9. here's the graph of f, which in this case is linear. Here's 3. And so now what I need to do is I need to solve for those two intersection points to get the corresponding x values. Those x values will give me delta. So here, I just want to say, okay, 12.1 equals 4x, because 4x is the formula for the function. So then just solve for x, right? Divide both sides by 4, I get 3.025, right? Over here, also, you have 11.9 equals 4x. Again, divide both sides by 4, and you get x equals, what do we get? 2.975, right? So those are the two values. And so then down here, right, these are really these two markings right here. So I have 3.025, and then over here, this one is 2.975 is this other point. So now I can see what that delta value is. To the right and to the left in either direction, I moved delta equals 0.025, right, to the left and 0.025 to the right. Right. So that's our answer in this case, right, to guarantee that the area of the unrolled rectangle of material is accurate up to epsilon equals 0.1. We must measure the base of it, right? The length of the unrolled material with greater accuracy, right? So you need a tool that measures down to 0.025 feet of accuracy, right? So that's our conclusion here, right? Now there's a nice takeaway from this. Notice what happened. We had a line that was slope 4, right? So the line of slope 4, what did it do? It magnified the input error by 4, right? So that's why epsilon, in this case, was exactly 4 times delta, because the error in the input got quadrupled in the output because the line was going up in slope 4. This is really nice because if you look at it, this is equivalent to just saying, if you do a little bit of algebra, right, you can say this is the same as if you divide both sides by epsilon, you get that 4 equals epsilon over delta. What is epsilon? It's really a change in y, right? And what is delta? It's really a change in x, right? And what is that? It's slope, which is 4, right? So that's at the end of all of that. That's a nice way to think of epsilon and delta. Now, if your graph isn't linear, then the connection between epsilon and delta isn't quite so clean, right? Because if it's not linear, now you don't have a consistent slope. Now the slope is kind of changing, right? But you can still think of it in the same way as far as solving for intersection points, and then finding a distance delta on either side of the graph. It'll just be a little messier. So, all right. So that's a little chat about the formal definition of a limit. Hopefully that demystifies that pile of symbols a little bit for you. Thanks.